Hello students, this is Mr. Deaver, and I'm here to talk to you about strong and weak acids. Now, last week we talked about how acids and bases are all around us and they're really important, and also how some foods are actually a little bit acidic, such as lemons, grapefruits, coffee, and even milk. Okay, so not all acids are equally dangerous, but why is that? Well, it has to do partially with how strong the acid is. So hydrochloric acid, or HCl, is a classic example of a strong acid, and it's something you definitely do not want to mess with. Vinegar, or acetic acid, is a great example of a weak acid, and it's obviously safe to use in food, although it does have a very sour taste, which we know is typical of acids, so it's definitely still acidic. Now, these acids, like most acids, have an H, and they also dissociate or break apart in water. And when they dissociate, they make a negative anion, in this case Cl, and that positive H plus ion reacts with water to form H3O plus, or hydronium. Now, as an aside, next time you want to change your password, make sure to set it to something like hydrochloric acid, because that would make it a strong password. Get it? It's a joke? Because strong acid, strong password. Okay, it's fine. Let's just move on. Okay, so by now, hopefully you've had a chance to explore the PhET. And what did you notice? Well, hopefully you noticed that in a strong acid, there's a much higher concentration of our products, of A minus and H3O plus. Now, as an aside, this A here is kind of like a variable, and it represents whatever the negative anion is of that particular acid, whether it's the Cl of hydrochloric acid or the NO3 of nitric acid. Also notice that when we check the solvent here, which is water, we see a lot of water molecules in both cases. Okay? Water is kind of like the background in which acid and base chemistry happens. So that background of water is not going anywhere. But back to the main point. It's especially easy to see if we look at the graph that with a strong acid, there's basically no HA particles because that acid completely dissociates, and we see a very high concentration of products, in this case A minus and H3O plus. But if we look at a weak acid, that HA particle only somewhat dissociates. So we see a much lower concentration of products, and we have a mix of HA, A minus, and H3O plus. Also, remember that this is a reversible reaction. See the double-sided arrow here? That means that the reaction can happen in both directions. And in fact, both reactions are happening at the same time all the time. However, with a strong acid, the acid completely dissociates, and the left to right reaction is favored, so we get a high concentration of products. With the weak acid, the acid only partially dissociates, so the right to left reaction is favored more so than with the strong acid, and we get a mix of reactants and products. If you think back to HCl and vinegar, if we dissolved HCl in water, we would see a very high concentration of these products. But with vinegar, which is a fairly weak acid, we'd see a higher concentration of the reactants. Now, we also asked you to explore concentration. So with a strong acid, if we change the concentration of the acid, notice that we still don't see any HA particles. The acid still completely dissociates, and all we get are H3O plus and A minus. It's just that as we add more acid and the acid gets more concentrated, the products also get more concentrated. With a weak acid, if we change the concentration of the acid, we still get the same proportion or the same mix of HA, A minus, and H3O plus. The acid still partially dissociates, but as we add more acid and the acid gets more concentrated, there's a higher concentration of just all the particles in general. So, to summarize, A strong acid is an acid that dissociates completely in water, and a weak acid only partially dissociates in water. A concentrated acid has a high molarity, which means there's many solute particles per volume of water. It's like there's a high density of solute particles. It's kind of like being in Manhattan on a busy Saturday afternoon. It is packed and also smelly and full of trash. A dilute acid has a low molarity, which means there's not many solute particles per volume of water. It's like there's a low density of solute particles. It's kind of like driving through Kansas. There's one person every 25 miles. You're bored out of your mind, and you just can't wait to get to a more exciting state. There's nothing there. There ain't nothing in Kansas. Okay, so this is not on your paper. However, we want you to draw this on a separate sheet of paper as we go through it together. So let's start with a strong concentrated acid. Because this is a concentrated acid, we're going to dissolve 4 HA molecules in this teeny little box, because that's a lot of particles in that little space. And because it's a strong acid, it's going to completely dissociate. So we're going to get all A- and HA particles here. Okay, and since I dissolved 4 HA molecules, I'm going to get 8 of these particles, 4A- and also 4H+. And just as an aside, remember that when we say H+, we really mean H3O+, or hydronium. Okay, now I want you to pause the video and try to draw the other 3 on your own. Okay, we're back. For a dilute strong acid, because it's dilute, we're going to add only 2 HA molecules to represent a lower concentration. But since it's a strong acid, it's going to completely dissociate, and both of those particles will break into A- and hydronium. So we're going to get, again, still all A- and HA, but just not as many of them because it's dilute. For a concentrated weak acid, again, because it's concentrated, we're going to add 4 molecules because that's a lot of particles in this little space. But because it's weak, only some of them will dissociate. So let's say that 2 of them do not dissociate here, and then 2 of them do. So we're going to get 2 HA particles, and then the other 2 are going to dissociate into A- and hydronium. Okay, with a dilute weak acid, because it's dilute, we're going to add only 2 molecules, 2 HA molecules, because it's a lower concentration. And because the acid only partially dissociates, because it's weak, let's say that one of the HA molecules dissociates and one of them does not. Now, it's important to note that in the concentrated weak acid, we still have a good number of H plus molecules here. In fact, with the way we've drawn it, we have the same number of H plus in the concentrated weak acid as in the dilute strong acid. So weak acids can still be dangerous if they're concentrated enough, and a strong acid will be less dangerous if it's more dilute. It's also important to note that even though we're focusing on acids here, this same principle applies to bases. Okay, time for some summary questions. Pause the video, answer these questions, and then come back. Okay, we're back. Now the key idea here is we want to say which is more acidic. And what makes something more acidic is a higher concentration of H plus ions. So between a dilute strong acid and a concentrated strong acid, which one has a higher concentration of H plus? The concentrated strong acid. So that is our answer. All right, between a dilute weak acid and a dilute strong acid, again, we want to go back and see which one is going to have a higher concentration of particles. Let's see, dilute weak and dilute strong. Right, well, the dilute strong has a higher concentration of HA particles, so that is going to be our answer. All right, between dilute weak and concentrated strong, well, pretty obvious here. This one's going to have a way higher concentration of H+, so that's going to be our answer. Now, between a dilute strong acid and a concentrated weak acid, It's going to depend on how strong the strong acid is and how concentrated the weak acid is. So we really can't answer that with the information that we have here. All right, hopefully you all enjoyed learning about strong and weak acids. See you later.